Hi everyone, welcome back. Today we are going to focus on section 12.5 where we will be discussing the equations of lines and planes. So to start off this discussion, what we're going to do is we're going to outline some of the items that we use for the equations of lines. Now, in algebra class, we know that the equation of a line could be of the form y is equal to mx plus b, where m is the slope of the line and b is the y-intercept that we are working with for that line. Now, equations in R space 3, or let's go ahead and specify this, equations of lines in R space 3 take on a similar form. Now, notice I said similar and not same. It's because when we are looking at equations of lines, we have to consider the equation of the line that is given in vector form. Simply because there could be different planes that contain this given line, or this line can have a direction that we need to identify. So on the screen here, you'll see that I have your coordinate system, the x-coordinate, the y-coordinate, and the z-coordinate. And what I want to do to start off is I want to create a very basic line. And by basic line, what I mean here is that I want to create this line in R space 3 that goes through the origin of my coordinate system. Now, this line I am going to go ahead and I'm going to just identify as L naught. So I drew a line here through the origin of my coordinate system, and again I'm going to call this line L naught. So what I want to do now is I want to use vectors to give more of a description for this line. Okay, so say that I took a vector, and let's call this vector V, just for argument purposes and to be similar to what your book has. So say I take vector V that starts at the origin and extends in some direction in which the line goes in. And again, we're just going to call this vector V. And I'm going to give vector V components A, B, and C. Now, notice, vector V is completely dependent now on what point lies on line L naught. In other words, that vector V is going to have a fixed length. Well, what if we want to, let's say, go around that? What if we some way, somehow want to create, or let's better yet say this, what if we want to use that vector V to show us that line? Well, one of the items that we can then say is we could just take vector V and we could start scaling vector V in some direction. So I'm going to call this new vector t times vector V. In other words, I'm going to scale that vector. So as it looks like on screen is that vector t times V starts at the origin and extends to the top right hand corner of the screen. And if I wanted to keep scaling it, let's say in the opposite direction, that way it would capture the opposite part of that line. In other words, the part that extends from the origin down to the left bottom of the screen. Well, then those values for t would then need to be negative. But how much or how many values do we then need to scale V by in order to generate the whole line? Well, that is here. I am going to use the scalar t Whoops, no equal sign there, my apologies. I am going to use the scalar t to say that t is unbounded. T is actually going to take on every single real number value between negative infinity and positive infinity. Therefore, vector tv, which is the scalar t multiplied by vector v, will then be able to generate this whole line L naught. Now, that's really amazing. Okay, so we're going to kind of keep that in our back pocket for now. And what we're going to do a little bit more is we're going to specify here that t times v, so scalar t times vector v, is actually denoted by the scalar t times a, the scalar t times b, and the scalar t times c. And again, this just goes because of scalar multiplication onto vectors. So this looks really great. Now, this only holds for certain lines that go through the origin, or that pass through the origin in this coordinate system. So now is where I kind of want to broaden my view. I want to broaden my view more specifically because now what I want to do is I want to start generating the equation of any line that exists in R space 3. Meaning these lines don't necessarily need to pass through the origin. So what can we do? Well, this is what I'm going to do. Is I'm going to take everything that I've built so far. I'm going to take my coordinate system x, y, z. I'm going to take my line L naught. I'm going to take my vector t times v and my vector v, and I'm going to reconstruct it on this other coordinate system. Okay, here we are. And what I'm going to do now is I'm going to select a random point in R space 3. So let's create a random point in R space 3. And let's go with the color red here. So here's my point. This point, let's call this P naught. This is going to have coordinates x naught, y naught, and z naught. So again, I'm creating this point that's out in R space 3 that is not on the origin, and it does not fall on my line L naught. So now we could then start talking about this. What if once we identified that point in R space 3, what if we then drew a vector to it? Or what if we then shot a vector to it? That vector we will then call vector R naught. Now, what is the coordinates, or sorry, what are the components for this vector? Well, we can extract those coordinates if we just do ending point minus a beginning in component form. Then we're going to be able to extract that specific vector. So this is going to be where vector R naught is going to be given by vector components x naught, y naught, and z naught. Awesome. So that works really great for us. Now, furthermore, what if at this point in time I said, you know what? I'm going to take line L and I'm going to shift line L so that line L naught so that it doesn't pass through the origin. Instead, now I am going to want that line to pass through the point P naught. So let's go ahead and let's get that done. I am going to take line L naught as it is here. All right, so here's my line. Making sure this is parallel and the exact same line. Okay, I think I got this. Okay, good enough. So I'm going to take this line L naught and I'm going to shift it upwards in order for that line to now pass through that given point. This line, notice, this line is not line L naught anymore because again it does not pass through the origin. So I am just going to call this line L. That's awesome. Now notice, because I shifted every single point on that line L naught up to that point P naught, now I also get to shift my vectors. And remember, vectors, as long as we don't change the direction or the magnitude, these vectors are going to be the exact same vectors. So what can we do? Well, we can still find vector V to begin at point P naught. That's great. And we could also find vector T times V on line L. I have no idea why the color's not showing. Okay, might be a glitch, it's okay. So we are able to again then extract that we do have vector V and we do have vector T times V occurring as well. Now, one thing that we want to point out as well is this. We want to point out that the value for T is going to be very specific. So I'm going to write that specification here. If the value for T is equal to 0, then the vector T times V will just condense down to the point P naught. Because again, we shifted all of the points up to that point P naught. However, if the value for T has positive values, well then, that is going to represent an increasing direction for this line. And these are greater than 0. The T value is greater than 0. Anytime that T values are negative, it'll generate the opposite side of that line. In other words, we are now able to generate this equation of a line using vectors. So what I want here at this point in time is I want to then start talking about the vector equation for line L. So vector equation for line L. Well, that vector equation, it definitely depends on some scalar t. So what I'm going to do is I'm going to write my vector r, but in this case, it's going to be r of t. Because again, that vector equation of the line is dependent on some variable t. Now, we're going to keep going. We're then going to keep on identifying. Well, we took the vector t times v, so I know I have that vector, and then I shifted that vector upward, or let's say I just shifted that vector to some point p naught. But then we transcribe that vector, or that point, into vector notation, which means that we shifted t times v to the vector, r naught. And this here, this is the equation of my line using vector form. That is amazing. So again, I want you to take a step back really quick, and I want you to see how this very much resembles all of the topics that you learned back in algebra class. Because in algebra class, the equation of a line has a slope and a y-intercept. And in this particular case, we have something very, very similar. Okay, we have something very similar. We have what is known as my scalar, my directional vector, and my initial vector, which means that is all that we need for this specific equation of the line. That is amazing. Let's go ahead and let's write this down. Okay, here we go. So I'm going to have the vector equation of a line. This vector equation of a line is going to be r of t, which is given by t times v plus r naught. So this is one of your, let's say, formulas or equations that we will be using in this course, and we will be using it quite a lot. So this is very super uber duper important. I will put a red asterisk at the beginning of this equation, because we are going to keep needing it over and over and over and over and over again until we are exhausted. So let's keep elaborating on that now. So let's keep going with that exhaustion. Now I'm going to keep working on the right hand side of my screen. Okay, so on the right hand side of my screen I'm going to keep going, which now I can then just keep on extracting what I have. So I have vector t times v, so that's going to be t times a vector v, which is vector a, b, c, plus vector r naught, where vector r naught we said is just x naught, y naught, and z naught in component form. That's awesome. Now let's go ahead and let's distribute my scalar. A times t, b times t, c times t, and then I still have plus the other vector, which was r naught. So what I have to do at the end is just add these components. So what I have here now, my vector equation of the line in component form will now be x naught plus a times t, will then be y naught plus b times t, will then be z naught plus c times t. Check that out. That is awesome. What this is here, this now tells me that my first component on screen here, this is the x component. Great. So I have an x component. What's the next component? Well, the next component is my y component. And finally, I have my last component, which is my z component. What does this tell us, though? This tells us another super duper important fact. This actually gives us the parametric equations. So parametric equations of a line. These parametric equations of a line are three different equations. The first one is the x component. This tells me that the x component is equal to x naught plus a times t. This also tells me that y is equal to y naught plus b times t. And it also tells me that z is equal to z naught plus c times t. Great. Now we have one more equation, or one more super duper uber important equation that we need to observe. And for that, I am going to keep working on the right hand side of my screen. Again, looks like there's a theme there, right? Just keep working on the right hand side. So let's keep working on the right hand side. So I'm going to take my components that I just extracted. So I'm going to take my x component, where I said that my x component was going to be equal to x naught plus a times t. And what I'm going to do here is I am going to solve for t. So solving for t, we get x minus x naught divided by a. This is equal to t. Okay, that's great, awesome. Let's keep that in our back pocket. Looking at the second component, I'm going to do the same thing. I'm going to start off by saying y is equal to y naught plus b times t, and I am going to take the same approach. I want to solve for t. In this case, if I solve for t, I get y minus y naught divided by b is equal to t. Now, you can figure out that the very last extraction, if we do the exact same thing that we did in these previous two components, that if we solve for t, that we get z minus z naught divided by c. Now, notice our t value is initially just one value that is the same value for all of the different components. So if t is 0, it must be 0 for all components. If t is negative pi, then t must be negative pi for all components. What this tells us is that all of these equations are equal to one another. And these equations are actually known as your symmetric equations of a line. So symmetric equations of a line. These symmetric equations of a line tell us that x minus x naught divided by a is equal to y minus y naught divided by b, which is equal to z minus z naught divided by c. And these three equations on the left-hand side of your screen are the ones that I classify as super duper uber important for us as we progress through the course. Not only will we see them in this particular section, we're also going to see them in chapter 13, again in chapter 14, again in chapter 15, and again in chapter 16. So at any given point in those chapters, we might be given the vector equation of a line, and we must know how to interpret that. We might be given the parametric equations of a line, and we must know how to interpret those. Or we might be given the symmetric equations of a line, and again, we have to know how to work with those. So this is now really interesting that we get to see this. Now, I am going to comment on here, and I am going to say that I want you to pay close attention to the symmetric equations of the line. Simply because if the symmetric equations of the line exist, then we must be able to extract them. And by that, I mean, let's track, let's go with b, that b coefficient. What if the b coefficient was 0? And it's completely possible for that b coefficient to be 0. However, when we work with a symmetric equation, we can't exactly divide by 0, right? We're not taking a limit here or anything, so that part will not be possible. Well, if that's the case, then we backtrack to the original equation that we were looking at, which is the parametric equation. If your b value was 0, you make that b times t be equal to 0, and you're only left with y is equal to y naught. Which means you don't really have a parametric equation to be equal to your middle component. Instead, the middle component will just be y is equal to y naught in the case that b is equal to 0. And similarly, you'll work with what happens if my a coefficient is 0 or if my c coefficient is 0. You're going to work with those different options, and again, we have to make sure that we analyze what it is that we're looking at and how it is that we're looking at it. Great. Now, just as a quick comment, on an exam or on a quiz, I will specifically ask you to generate the equation of a line in R-Space 3, and I will ask for one of these specific forms. I will say give your answer as symmetric equations of a line, or give your answer as parametric equations of a line, or give the answer in a vector equation of a line. So you must be, again, well versed in those three equations. That is great. That is awesome. I really like that section, or that part for this section. So for this example, we then want to find the parametric equations for the line through the point P, which is given by coordinates 1, 0, 2, and Q, which is given by 2, 5, negative 1. And then what we want to do is we want to use the parametric equations to find parametric equations for the line segment PQ. Okay. Now again, we want to spend some time and we want to analyze what it is that we are observing, or what it is that we're trying to extract. Now, if you need time to write the question, then by all means press pause on the video, and once you're done writing the question, then you can unpause and you'll catch up. Now, one of the items that I definitely want to discuss before we start that question is, wow, I have no idea why my computer did that. Okay, so here we go. One of the items that I do want to discuss here is, what do we need to generate the equation of a line? At the end of the day, what is the most basic items that we need to generate the equation of a line? Well, there are only two things that we need. Number one, we need a vector v. Once we have a vector v, we know we'll scale that. So scaling, we don't necessarily need to know right away. We just need to know what is vector v. In other words, we need a directional vector. So that's number one, directional vector. Got it. Number two, once we have that directional vector, we then need to shift that directional vector. And we need to shift it onto some point. In other words, we need to know what is one point on the line in question. And those are the only two things that we need. We just need a point on the line and a directional vector. That's it. No more. We don't need anything else. We can extract other items, that's awesome, but at the end of the day, we only need those two basic things. So in order to start this problem then, I am going to say that I need these two things. I need the first thing, which is a directional vector. Okay, and we're going to call this directional vector v. Okay, so I just need that directional vector. Number two, I am going to need a point on the line. Now again, this point on the line we could just call P naught or Q naught or whatever it may be, just some random point on the line. Now again, I want you to notice those similarities back to algebra class. To create the equation of a line in algebra class, what did we need? Well, we needed a slope and we needed a point. As soon as we had those two things, awesome, we generate the lines all day long. And that's exactly what we want to do here. Identify those two basic items, directional vector, point on the line, let's get it, and let's keep going. So in order to do this, we are given 2 points on the line. So we are given those 2 points. All we need to do is choose one of the points, and that will then become the point on the line in question. So we are free to choose whichever one we want. Does not matter. Okay, so if we were in class, I would then ask you all to then choose, do we want to work with P or do we want to work with Q? And then somebody would answer, I want to work with Q, or something like that. So I would say, okay, great, let's work with Q. So I know I found my point on the line, and I'm going to classify that as vector Q, or sorry, point Q, which will be 2, 5, and -1. So I'm going to keep that in my back pocket. Next, I will say, let's grab a directional vector. Now, the nice part about vectors is that it does not matter where they begin, so long as they have the same direction and magnitude. So, in order to find my directional vector, it will not matter if I start at point P and shoot a vector to point Q, or if I start at point Q and shoot a vector over to point P. In other words, what I'm looking at here for my directional vector, I can either use vector PQ or I can use vector QP. And again, it does not matter. So if we were in class, I would then ask you all, do you want to work with vector PQ or do you want to work with vector QP? And somebody would probably say, I want to work with vector QP. Awesome, great, great, great. So we're going to be working with vector QP, and we're also going to be working with the point Q. So let's go ahead and let's finish finding that directional vector. So directional vector here, I'm going to call that directional vector V, and that's going to be the vector from Q to P. How do we find vectors between points? Well, we do ending minus beginning. Since the vector in question is going to start at point Q and it ends at point P, I'm going to do every component in point P minus every component in point Q. In other words, the x component is going to be 1 minus 2, which is -1. The y component will then be 0 minus 5, which gets me -5. The next component will then be 2 minus -1, which will get me 3. Great. So I have my directional vector. Awesome. Now I have my point on the line. So since I have my point on the line, I can now generate that vector that will be shot from the origin to that point. In other words, it's going to give me my displacement vector. And that's what I really need this point on the line for. So this point on the line now becomes, so magically it's going to become vector R0, and this vector, again, is going to be shot from the origin to point Q, which will just be 2, 5, -1. Look at that. That's looking great. So this is now my x0, y0, and z0. My directional vector gave me my A, my B, and my C. Now the big question was that we need to find these parametric equations. And that's what I want to do here. Let's give those parametric equations. Parametric equations. Here we go. So, according to the work that I had previously done, the one where I boxed my answers up there, where I showed the 3 super duper uber important equations, parametric equations was the middle one that we worked on, and that gives that my x component must be equal to x0 plus a times t. So as I'm looking at my parametric equations, my x component is going to be x0, which is 2, plus it's going to be my a value multiplied by t. So in this case, I actually get negative t. There we are. My y component is then y naught, which is 5, plus b times t, where in this case it's going to be minus 5 times t. Okay, that's great. Let's keep going. Next component, z is going to be z naught, which is negative 1, and then we have minus c times t, which in this case is going to be 3t. Or, sorry, did I say minus? I meant plus. My apologies. It's just the other ones were minus. This one is not. This one is negative 1 plus 3t. There we go. And now this works where my t values are unbounded between negative infinity and infinity. They must be scales, or they must be scalar values for t, and again, t is unbounded. So here we have our answer for the first part of the question, that we are looking for these parametric equations. Awesome. So again, that answer was given here. Now for the second part. The second part kind of seems a little redundant in saying, well, why do we now need to find the parametric equations again for the line segment? Well, there is a discrepancy there, and the discrepancy is in the verbiage that is given to us. The verbiage for the very first question was that we needed to find parametric equations for the line. That's the whole line. The verbiage for the second question says use the parametric equations to find the parametric equations for the line segment. A line segment is just a piece of the line, not the whole line. In other words, our t values, our scalar values, will now have to be bounded. So, I hope that you all can agree with me that if I want the parametric equations of a line segment, then the x, y, and z components are all the same. We don't need to rehash all of the work because it's already done. All we need to do is bound the t values. So let's start working on that here. So I'm going to just re-summarize this. Parametric equation. And this is going to be for the line segment. PQ. Okay, so again, I have the exact same x component, which is 2 minus t, the exact same y component, which is 5 minus 5t, and the exact same z component, which is negative 1 plus 3t. Now, you might be saying, okay, Mr. Castro, why or how are we going to get those t's to be bounded now? Well, that, my friends, is very, very straightforward. I want you to then think about what t values will then get you the first point, a point of 1, 0, 2, and what t values will then get you the point of 2, 5, negative 1. Because these points are on the line, hence they must be on the line segment because they define the ends of the line. So if we can find what t values satisfy these parametric equations to give us these answers, then our job is done. So, you'd be surprised how straightforward this is. Let's go find it. So, looking at my parametric equations, what t value do we want to substitute? Well, one of the easiest t values to substitute is t is equal to 0. If t is equal to 0, look at your parametric equations. We get x is equal to 2, y is equal to 5, and z is equal to negative 1. That's point Q. So one of the items that I get here, one of the things that I get here is that when t is equal to 0, we get x is equal to 2, y is equal to 5, and then z is equal to -1, which is point Q. Great. Okay, so we found one of our parameters. T is equal to 0. Okay, awesome. So is there going to be another value smaller than that, or is there going to be a value larger than that for t? Well, we now need to find that out. So we know that we found the t value that gets us point Q. Let's find point P now. What t value can we then substitute in order for that t value to simplify those parametric equations to get us point P? Well, when, it looks like it's another easy one, when t is equal to 1. X is equal to 1, y is equal to 0, and then z is equal to 2, which is point P. Check that out. Isn't that amazing? Gosh, I love this stuff. In other words, our parameters, or our parameter t, is then bounded by 0 and 1. And that is no coincidence. That is no coincidence whatsoever. Any time that you want to find the parametric equations of a line segment, all you have to do is find the initial parametric equations between the points that you were given, and then bound your t values between 0 and 1, and you're done. Now, if you're using the Stewart book, Stewart doesn't tell you that. Stewart does a whole roundabout way, and it's a little bit honestly confusing the way Stewart does it. However, if you're not using the Stewart book, then that's awesome. Again, there's still sort of a roundabout way about it, but nonetheless, at the end of the day, we still get the exact same equations. So I want you all to then remember that when it comes down time for, let's say, an exam, because at the end of the day, parametric equations for a line segment are the exact same thing for parametric equations of a line. The only thing that's different is you must parameterize, or you must bound your parameter. Awesome. Let's do an example now where we are going to look at an example of two different lines, and we are going to try to determine if those two lines then intersect. All right, so by the use of internet magic, I will produce that example in just a few seconds. Awesome, so here we are. The question is, determine whether the following two lines intersect. Okay, so again, we want to make sure, or we want to investigate whether these two lines intersect. Now, by the depiction that we have where we first started, where we said, okay, we generated the equation of the line by finding a directional vector and then finding a point where we would shift that initial line to, or in this case, a point on the line in question. So our t values definitely depended on whether the values were going to, where the values were going to be centered for those vectors of that equation of the line. Now, it would then stand to reason that if there is another line intersecting a given line, then at some point in time, or at some point in space, those t values must be exactly the same. So what does that mean for us? And coming over here, R1, I'm going to label t sub 1, and R2, I'm going to label t sub 2. This way we can identify that the t values are not necessarily the same. However, if we can find one point in space, in R space 3, then that means the t values will then intersect. Sorry, the t values will be the same, therefore the lines will intersect. So in order to start this process then, we are going to consider R1, vector R1 of t sub 1, being equal to vector R2 of t sub 2. And again, this is because we want to find out, does this happen? Well, now we have to equal the components to one another. So what I'm going to do here then is I'm going to take the vector components in R1 and I'm going to already combine them using addition. So my x component will be 1 plus 3, 1 plus 3 times t sub 1, comma. Next component, the y component, will be just 3 times t sub 1. The next component will then be 1 plus 5 times t sub 1. And this is vector R1. R1 must be equal to R2 if they intersect. So the vector equation for R2 will then be 3 plus 4t2, 6 minus 2t sub 2, and then the last component is 1 plus 7 times t sub 2. And again, if two vectors are equal, then that means their components must be equal to one another. So in that extraction, I now get that 1 plus 3t1 is equal to 3 plus 4t2. I also get that 3t sub 1 must be equal to 6 minus 2t sub 2. And I also get that 1 plus 5t sub 1 must be equal to 1 plus 7t sub 2. There we are. So again, if they're equal, if these two vectors are equal, then these parametric equations must be equal to one another, which in turn, we should be able to find a certain value for t sub 1 or t sub 2, simply because as a result of this, we have 3 equations and we have 2 unknowns. So we have more than enough tools at our disposal to solve for t sub 1 and to solve for t sub 2. So let's get started. I'm going to work with the very first equation. So the very first equation, that's what I want to work with. And I can either solve for t sub 1 or I can solve for t sub 2. The choice is really up to us. Now again, if we were in class, I would ask you all to choose what variable we want to solve for. However, since you all are not in here, that is completely fine. I'm going to subtract 1 from both sides, which will get me 3 minus 1, which is 2, plus 4t2, and then divide by 3 so that I can solve for t sub 1. So this is going to be 2 plus 4t sub 2, all divided by 3. There we are. Looking good so far. Okay, next one. I'm going to solve the second equation. Now, for the second equation, what I want to do now is I want to insert what I just found. Or in other words, I want to use substitution. So let's go ahead and let's use substitution here in this equation. So making that substitution then, I'm now going to get 3 times t sub 1, but t sub 1 is this 2 plus 4 t sub 2 divided by 3, and then equals to 6 minus 2 t sub 2. Notice the 3's will cancel within that substitution, so now we get 2 plus 4 t sub 2 is equal to 6 minus 2 t sub 2. That's awesome. So solving this, I can now get 8 t sub, whoa, I said 8. I don't know why I said 8, everybody. My apologies. 6 t sub 2. There we go. So 6 t sub 2. There we are. And then 6 minus 2, that should get us 4, which means t sub 2 is now going to reduce to 2/3. That is great. Okay, now that I have this value for 2/3, I can then resubstitute this. I can then resubstitute this back into the equation that I initially found for t sub 1. So this is now t sub 1 is equal to 2 plus 4 times 2/3 divided by 3. Wow, that 2/3 does not look good there. My apologies. There we go. Okay, great. So I'm going to go ahead and solve for t sub 1. Let's say I multiply both numerator and denominator by 3. So that's going to be nice. That's going to be 6 plus, that's going to be just 8, all divided by 9, which means I should get 14 over 9. Great, great, great. All right, looking good so far, looking good so far. Okay, so now that I have these two values, I now have t sub 1. So t sub 1 is equal to 14/9 and t sub 2 is equal to 2/3. So I have this third equation that I haven't really used. And if, big ol' if these two lines intersect, then that means the final components, the equations for the final components must be equal to one another for the t values that I just found. So what I'm going to do is I'm going to conduct more of a check. The check is, do these two numerical values that I found for t sub 1 and t sub 2 satisfy this third equation? If the answer is yes, well, the two lines intersect. If the answer is no, well then I'm sorry, the two lines do not intersect. And let's go ahead and figure that out then. So let's make those substitutions here. So 1 plus 5 times t sub 1, this is 14/9, is possibly equal to, I'm going to put a question mark because I don't know there, plus 1 plus 7 times t2, which is 2/3. Notice the ones will cancel. So the ones are going to cancel, that's nice. And now we're left with 5 times 14, which is 70. So the left side is 70 over 9, and the right-hand side is going to be 14 over 3. Notice these two are not equal. Sorry, everyone, but these are not intersecting lines. So to summarize this, the two lines do not intersect. Okay, so we now have to get into more of a deeper talk, because in R space 2, in other words, in the x and y coordinate system, if two lines don't intersect, then naturally the extraction that we get from that is that they must be parallel. However, these two lines are not parallel. Why are they not parallel? They don't have the exact same directional vector, so that's key number 1, that these two lines are not parallel. Okay, so they're not parallel, yet they don't intersect. Okay, so we have a small issue. Now, let's go ahead and let's visualize this. In order to do this, I'm going to need the help from my friend GeoGebra. So follow me along to GeoGebra. Here we are, my old friend GeoGebra. I went ahead and I inserted the equations of the lines. If you look on the left-hand side of the screen, you have the equations of those lines that we were working with. And the GeoGebra uses lambda as a scalar. Now on screen, you'll see that we have those two equations. And those two equations of the lines, the way we're looking at this kind of looks like they intersect. However, if we start skewing our view just a little bit more, you will then see that those two lines do not intersect. These lines are called skew lines. They are not parallel, but they do not intersect. These lines exist in two different planes, and they are not parallel to one another. So that's very interesting to see now that, again, because we have this new added axes, these two lines, again, if we were looking at them in R space 2, yeah, they would look like they intersect because they would. However, in R space 3, I'm sorry, that's a big no. These lines are skew. So this is the visualization that we get for these parametric equations of the line, that they do not intersect. Okay, so that's awesome. I hope you enjoyed that visual. Now let's go back onto our class to make sure that we finish rounding out this section. And what we're going to be talking about now for the last part of this section is going to be the equations of a plane and how to find them. So let's go back and let's start that interesting conversation. Okay, here we are. So I'm just going to circle that. The lines do not intersect. Okay, great. So let's start talking about this equation of a plane. And what I'm going to do here is I'm just going to generate just some random plane that we're going to be able to extract. All right, so there's one, here's one. All right, there we go. And there we go. So all I'm doing on screen is just creating this rectangular figure that will represent a plane. Okay, awesome. So what I want to do at this point in time is just identify that this is some plane, and let's just call this plane some plane P. So this is some plane P. Now, if I have a plane P, then that means that I will be able to find a normal vector to this plane. So that's what I want to identify here, is that I want to start off by saying I want to extract a normal vector to this plane. Now again, because we're given the plane, then that means we must be able to find a normal vector to that plane. So this is going to be my normal vector. I'm going to call that n for normal, and I'm going to give this components a, b, and c as such. Now what I'm also going to do is I'm also going to, I forgot to put a 90-degree angle here. There we go. Now what I'm also going to do here is I'm also going to find a vector on this plane. So on the plane P, I just want to identify some random vector on this plane. And this random vector, quote unquote random vector, is going to be, let's say, a nice vector. Okay, so here's the vector that I'm looking at. I'm going to give this vector certain coordinates. I'm going to say that this vector originates where the normal vector starts, and that's going to be at P naught, which is going to be X naught, Y naught, and Z naught. And it ends, in other words, the terminal point is going to be point P, which will be X, Y, Z. So now I can then start extracting what is this vector. So I'm going to say on the left-hand side here, or you know what, I'm going to say at this point in time, I'm going to move this really quickly. There we are. So what I'm going to say now is that vector P naught to P is one of the vectors that I want to extract. So vector P naught, beginning at P naught, ending at P, this is going to be vector ending minus beginning components. So this is going to be X minus X naught. So X minus X naught, then Y minus Y naught, and then Z minus Z naught. Okay, great. So once I have this, I can also start extracting my normal vector, but the normal vector is one of the vectors I already have. So that's my normal vector. Call it n. And this is A, B, C component form. Okay, so again, normal vector to the plane P, and then vector P naught to P is on the actual plane. So what I want to extract now is that because vector P to P naught exists on the plane P, and there is a normal vector which we identified as n to the plane P, that must tell us that vector n and vector P to P naught must also be perpendicular to one another. Or in other words, they must be orthogonal. So I'm going to say here, notice, all right, let's actually do this in a different color. I'm going to say notice that n and vector P naught to P are orthogonal. But now the question is, what do we know about orthogonal vectors? Well, if you think back to section 12.3, when we were dealing with dot products, we know something very specific about the dot product of two orthogonal vectors. Well, from section 12.3, orthogonal vectors have a dot product of 0. So that means that I can now take the two vectors that I have built here and take their dot product. So now I'm going to take vector n, and I'm going to take the dot product with vector P naught to P, and this dot product will be equal to 0 because they are orthogonal vectors. So naturally now I will have vector A, B, C dot vector x minus x naught, y minus y naught, and z minus z naught is equal to 0. And we can keep going. So let's keep going. Let's keep taking this dot product. This will now give me A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. And depending on which book you are using for calculus, some books will tell you, hey, this is the equation of a plane. And you know what? They are absolutely correct. Because the point x, y, and z, that point x, y, and z is going to be the variables that exist on that plane, where the points x naught, y naught, z naught are just going to be a random point on that plane. The coefficients a, b, and c now start extracting to be the normal vector to that plane. That's still pretty mind-blowing. Okay, so let's keep going then. Let's keep extracting. Let's see where I want this to go. All right, so what I'm going to do is I'm going to distribute my coefficients a, b, and c. So let's distribute. So I have ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. And then I want to get all the variables by themselves on one side. If they have coefficients, then that's great. I have ax plus by plus cz is equal to a times x naught plus b times y naught plus c times z naught. Check that out. Oh man, this is awesome. Finally, we can say we're left with this equation, which is ax plus by plus cz is equal to d, where the constant d is equal to a times x naught plus b times y naught plus c times z naught. Check that out. Amazing. That is the equation of the plane. More importantly, that is the equation of the plane using vectors. More importantly, that is the equation of the plane using vectors And it's the exact same equation of the plane that we found back in algebra class. Or not really found, more of it was given to us. Wow, that is truly, truly amazing. I love it. Every single time I see it. This is why I love teaching multivariable calculus. Because every time that I see this, I still get the warm butterfly feeling in my stomach that, wow, this is amazing. Now, this is all great. This is all fine and dandy. However, I want you to focus on that coefficient for D. So focus on that coefficient for D. Notice D coefficient is actually broken up just a little bit further. Now, your books might not tell you this, but I am. I'm going to give you this shortcut because I love this shortcut. All right. So here's my shortcut. Notice, or note, coefficient D, which is given by A x naught plus B y naught plus C z naught. This is actually a dot product. Look at that. First term is made up of two different factors, added to a second term that has two different factors, added to a third term that has two different factors. If we decompose A times x naught plus B times y naught plus C times z naught into a product of two vectors, where one vector is vector A, B, C, and the other vector is x naught, y naught, z naught, check that out, we actually have a dot product. More importantly, we know what vector ABC is. Well, initially that's the normal vector, so we get a normal vector dot, now vector x naught, y naught, z naught. Well, we don't really have a vector x naught, y naught, z naught, but we do have a point, p naught, that has those coordinates. In other words, this vector x naught, y naught, z naught is the vector that's made by the origin, from the origin to point p naught. This is coefficient D in its most decomposed form. I love that. So, since you're watching these videos, wow, I can't talk. It's very late at night. So, since you're watching these videos, that means you're probably taking my class, which means when I ask you to find the equation of a plane, and you're able to extract, number one, a normal vector, number two, a point on that plane, then to build the equation of the plane, all we really need is what is A, B, and C, in other words, normal components, or sorry, normal vector components, and we need to know what is the point on the plane, but we can convert that point on the plane into vector form. As soon as we find that, we have everything that we need. So, some instructors, again, present this in a different way. I'm not one of those instructors that want to present it to you in the exact same way as your book does. So I like to view things a little bit differently and find certain aspects of math that make it easier for us to understand. Now, what I'm writing on screen right now is an example that says, find an equation of the plane through the point P naught, which is 3, 1, 0, with normal vector, we're going to call this n, which is given by 3, 2, -5. All right, awesome. So again, find the equation of a line. So find an equation of the, find an equation of the plane. Now, finding the equation of a plane slightly different than finding the equation of a line. In order to find the equation of a line, we needed two items. Number one, a directional vector. Number two, a point on the line. Very similar items here for the equation of a line in for the equation of a plane in R space 3. Number one, we need, let me do this. What do we need? So we need number one, a point on the plane. That's one thing that we need. And number two, we need a normal vector to the plane. Those are the only two items. So when you're working a problem like this, either on the homework, on a quiz, or on an exam, it's always beneficial to write down what do you need. This way, once you start working with these problems, and some of these problems might get a little bit more complex, but when you're working with these problems, you at least know the foundation of what you're looking for. That in itself will be very beneficial. That way you don't get lost in the whole concepts of what am I looking at, what is this, I don't even know where to go. If you have those basic concepts, then again, you're going to do well. So let's keep going. Now I'm given a point, so I'm given the point on the plane, so that's awesome. And I'm also given my normal components. So your normal components given, that's your A, that's your B, and that's your C. So according to the equation of the plane, we have AX plus BY plus CZ. So given this normal vector, great, I got it. So I'm going to have 3x plus 2, I wrote 2b, plus 2y minus 5z is equal to, now I need my D coefficient. Well, remember what I said, that D coefficient is really just the dot product between two vectors. So this D coefficient is a dot product between the normal vector, which is 3, 2, negative 5, and the point in question, or the point given to us on the plane in vector form, which is 3, 1, 0. All I have to do is simplify the right-hand side, and we're done. So let's find the dot product for the right-hand side. Dot product for the right-hand side, 3 times 3 is 9, 2 times 1 is 2, negative 5 times 0 is 0, so it's really 9 plus 2, which is 11. There you are. No fuss, no muss. Got it all. Isn't that amazing? Gosh, I truly love math. Okay, so yay, here we go. Now, I want to show you something really, really neat, or something that I find very, very neat. Normal lines or normal equations have always been given to us. We just didn't know what they were. That's interesting. What do I mean by that? So, let me give you this example. From algebra. The equation of, let's say, a line is y is equal to mx plus b. Okay, great. Yes, we all knew that. That's one of the forms. However, another form, also, we have ax plus by is equal to c. This is standard form of an equation of a line, whereas y is equal to mx plus b is slope-intercept form. Okay, so we know this to be true. Now, what if I gave you a line that said from algebra class y is equal to, let's say, 2/3 x plus 5? Okay, well then you would say, all right, Mr. Castro, yeah, we know how to interpret that. That would be your y-intercept is 5 and you have a slope of 2/3. And I would say, yeah, that's awesome, that's great. Now, I would then also say, find me a line that has a slope that's going to be orthogonal to that line. Well, the work is actually what we know to be the equation of a plane. But really, if we extract this last component, or if we nix this last component, the z component, we're really just left with the equation of a line in R space 2. So what does that mean for this line? Well, that means for this line, if I multiply both sides by 3, I get 3y is equal to 2x plus 15, which naturally then gets me negative 2x plus 3y is equal to 15. Check this out. this here a normal vector, a normal vector to the line y is equal to 2/3 x plus 5 is normal vector here, first component -2, second component 3. There we are. Now, what does the slope look like? Well, if the slope is x and this is y, so this would be 3 divided by -2, which coincidentally is just the inverse of the slope that we have here. Wow, look at that. So even back in algebra class, we were given these normal vectors. We just didn't know how to interpret them. Or in a certain instance, we didn't explain that portion because, again, we weren't dealing with vectors at the time. However, it's always been there. Isn't that amazing? Wow. Again, it always amazes me. I love this stuff. So, here we go. Next example. I hope you're all still following me. So, here we go. Let plane P, that's just a fancy looking capital P. Alright, so let plane P have equation 7x minus 4y plus 2z is equal to -10. And we want to find an equation of the plane parallel to plane P. Let's get that fancy capital P here. Passing through part A, the origin, and part B, this is going to pass through point Q, which is given by 2, -1, 3. Alright, so take some time, write the question down. Alright, so here we go. So we have, again, plane P. And what's really nice about plane P in this particular case is that given the equation of the plane, we automatically get the normal vector to that plane for free. Okay, so a lot of people say, oh, nothing in life is free. Well, guess what? The normal equation, or sorry, the normal vector to a plane is free whenever you're given that equation of a plane. So that's awesome. Now, my normal vector that I am given here is going to be 7, -4, and 2. So let's write that down. 7, -4, and 2. There we are. Okay, great. Now, part A. For part A, what I want to do is I want to now create the equation of a plane that is going to be parallel to plane P. Okay, so I want you to now try to envision this. If two planes are parallel, do they have the same normal vector? In other words, if two planes are parallel, must the normal vectors to those planes be parallel as well? Well, the answer to that is yes. If two planes are parallel, then their normal vectors orthogonal to each respective plane must also be parallel to one another, which means we can use the same vector. So the normal vector for part A is going to be the same vector that I extracted, which is 7, -4, and 2. Now, I just need a point on that plane that I'm trying to construct. But they're telling me it's going through the origin, which means if it's going to go through the origin, then I need point P, which will be 0.000. So in order for me to extract the equation of this plane, I now need ax plus by is equal to d. Ax, so that's going to be 7x minus 4y plus 2z is equal to the normal vector. So the normal vector, which is 7, negative 4, 2, dot the last vector, or the point in vector form, which is 0, 0, 0. So what's the equation of the plane? So that's 7x minus 4y plus 2z is equal to 0. This is the equation of the plane that is parallel to the given plane, but this plane that we constructed goes through the origin. Awesome. Isn't that amazing? Loves this stuff. Part B. We're using the same normal vector. Again, we want to find the equation of a plane parallel. So again, parallel, same normal vector. So same normal vector, 7, negative 4, 2. However, now we need a point, and the point here is point Q. That's going to be on the plane that we are looking at. Naturally, normal vector goes back to the coefficients for the plane. So this is 7x minus 4y plus 2z is equal to Q. Well, not exactly Q, but it's equal to the dot product of the normal vector and the vector shot from the origin to point Q, which means that's vector 2, negative 1, 3. All I need to do is simplify. 7x minus 4y plus 2z is equal to this vector, or sorry, to this dot product, that's scalar. So it's going to be 7 times 4, that's going to, or sorry, 7 times 2, that's 14. Negative 4 times negative 1, that's 5. So far 19. And then 2 times 3, that's 6. So 19 plus 6, sorry, 14, sorry, 18. 18 plus 6, that's going to get us 24. Which means there's our answer. The plane that is parallel to the given plane, but our plane goes through point Q, which is at 2, negative 1, 3. That equation is 7x minus 4y plus 2z is equal to 24. And look at that. We're just trekking along. Isn't this amazing? Next example. We want to find an equation of the plane, let's say the plane P, determined by the points P, which is 1, 0, negative 1, Q, which is 2, 2, 1, and R, which is going to be 4, 1, 2. Just like this. All right. So we got some work ahead of us here. And again, we mustn't be afraid to tackle that work with very, very long technical calculations. So we want to find the equation of the plane. And again, in order to find the equation of the plane, we just need two different items for the equation of the plane. So for the equation of a plane, we need, number one, a normal vector to the plane. And number two, we need a point on the plane. So the point on the plane, we actually have our choice. We could choose point P, point Q, or point R. Either one of those three would suffice. So the point on the plane, we have options. However, the normal vector to the plane, we don't have that option. We need to construct that, or we need to find that. So let's go through and let's start brainstorming some ideas. If we have 3 points on that plane, how can we then extract, some way, somehow, with all the tools that we've developed so far in the previous sections, how can we extract a normal vector? Well, we can start by shooting a vector from P to Q, and then another one from P to R, or from Q to P, or Q to R, or R to Q, or R to P, whatever combinations you want. So yes, we do need vectors here. Now, for the sake of argument here, let's say that I look at my points like this. And on screen I just drew 3 random points. So say that I had one vector and another vector here. As such. So let's say I center them at point Q. It's not necessary to center them at point Q, or in other words, to have a vertex at point Q. It doesn't matter where the vertex is at, as long as it's one of the points. So say that I had 2 vectors that I was able to extract from these 3 points, which we can. There is a certain section that we dealt with, which was a section that allowed us to generate a certain vector that is orthogonal to both vectors in question. What was that called? Well, that normal vector, or that orthogonal vector, is known as your cross product. Which means we now need to construct 2 vectors from the 3 given points. Once we find those 2 vectors, we then need to find the cross product between those 2 vectors. That then will give us a vector that is orthogonal to both vectors. But since both of the initial vectors are on the plane, that normal vector, or that cross product, will then be orthogonal to the plane. Awesome. Look at that. Now we're rolling all these sections that we learned into this one section. Oh man, that is beautiful. Beautiful, beautiful. So let's keep going then. I just realized my computer's low on charge. So what I'm going to do really quick is I'm going to put pause on the video. I'm going to come back and it'll be charged. All right, I'm back. So here we go. Let's, since on the drawing here on screen, I have my vertex at point Q, I kind of want to stick with that whole process. So I am going to go ahead and say vector QP. I am going to call this vector A. Vector QR, I'm going to call this vector B. Okay, so here we go. Vector A is made by QP. Again, ending minus beginning. So ending minus beginning. So 2 minus 1, that gets us 1. 2 minus 0, that gets us 2. 1 minus negative 1, that's another 2. Vector B will then be the vector from Q to R. So again, ending minus beginning. So 4 minus 2, that's 2. 1 minus 2, that's negative 1. And then 2 minus 1, that's going to be 1. So awesome, we built these 2 vectors. Now what we need to do is we need to take the cross product for these 2 vectors. So let's go ahead and let's take that cross product for those 2 vectors. So taking the cross product will result in a normal vector. So I'm going to say here on screen that normal vector, in other words n, is going to be given by the cross product of A cross B. And again, this is going to have an I component, a j component, and a k component. Vector A is 1, 2, 2. Vector B is 2, negative 1, 1. So the I component, that's going to be 2. So 2 times 1 minus 2 times negative 1. So that's going to be 4. All right, looking good so far. Minus the j component, that's going to be 1 times 1, that's 1, minus 2 times 2, that's 4, so that's going to be 1 minus 4, so that's going to be negative 3. k component. For the k component, we are going to have 1 times negative 1. So that's going to be negative 1 minus 2 times 2 is 4. So that's going to be negative 1 minus 4. That's going to be negative 5. So here's our normal vector, which is component form. That's going to be 4, 3, and negative 5. And again, it's 3 because the middle component is negative times a negative, which means we found a normal vector to the plane. Awesome. So we have everything that we need. All we got to do now is roll it all into that equation. So the equation of the plane here, I'm going to work on the right-hand side now. The equation of the plane is going to be ax plus by plus cz, where a, b, and c come from the normal components. So my normal components here is 4, 3, and negative 5. So that's what I use. 4x plus 3y minus 5z is equal to the dot product of the normal vector. So the dot product of the normal vector, that's 4, 3, negative 5, dot the point on the plane in in vector form. Now, because we have our choice to choose P, Q, and R, you're more than welcome to choose any one of those points. Simply because we centered our vertex for these two vectors at point Q doesn't mean that we have to use point Q as our point on the plane. We could choose point P or R. If you're not sure you believe me or not, let's go with the point R. Alright, so I'm going to choose point R in vector form. There we are. Which means the equation of the plane, once you take the dot product, this is going to be, let's say, 16. So 4 times 4, that's 16, plus 3, so it's going to be 19. And then 19 minus 10, well, 19 minus 10, that should get us 9, which means this is the equation of the plane. This plane contains the points P, Q, and R that were given to us. Now again, naturally, you could have chosen, let's say we could have chosen point P, and we would have substituted, instead of vector R here, we would have substituted vector P. It still would have given us the exact same answer. Or if we would have chosen point Q. That's the nice part about these types of equations when we're finding these equations of the plane. Pretty good so far. Everything's nice, neat, concise. Next example, I want to find the point P where the plane, which is 3x minus 9y plus 2z, is equal to 7, and the line r of t is equal to 1, 2, 1, vector form, plus t times negative 2, 0, 1, intersect. So we want to make sure that we find this point of intersection between the plane and this line. Okay, so in order to do this, what we're going to do is we're going to try to visualize this. Okay, so we have the equation of a plane. So what I want you to do is just, again, try to visualize a random plane. And let's see if we can extract this. All right. So here's my plane. There we go. So we have some plane here, and we know that we're going to have some line that's going to be intersecting this plane. Okay, so I'm just going to draw a line here. This is going to be the line here, moving in that direction. And then once it intersects the plane, then we'll see it from below. There we are. All right, so there's some line, some vector equation of the line that we are going to be working with. And this is just another plane. Now, in order for this to happen, that means that the components for my line, r of t, must be equal to the components of the equation of the plane. Well, we then need to extract what are the components of the vector equation of the line. So the components for the vector equation of the line, those are going to be the parametric equations. So I'm writing the parametric equations of the line, and that's the line that's given to me. I have that x component is equal to 1 minus 2t. So 1 minus 2t. I have that the y component is equal to 2, and it's really 2 plus 0t, but that's just 0t. And then 1 plus t for the z component as such. Excuse me. So these components must be equal to the components that are given to us on this plane. So what I'm going to do now is I'm going to reinterpret this using the equation of the plane that's given to me. That's 3x minus 9y plus 2z is equal to 7. I'm going to make my substitutions. The x component for the parametric equation of the line is 1 minus 2t. The y component for the parametric equation is just 2. And then the z component is 1 plus t. And all of this is equal to 7. Which means I am able to find what t value, for which t value, does this parametric equation of the line intersect this plane. And that will then be able to transcribe into some point on that plane or some point on that line. So let's distribute here. So this is going to be 3 minus 6t minus 18 plus 2 plus 2t is equal to 7. Okay, now I'm going to go ahead and add here. So this is going to be negative 4t is equal to, and then I have 7, and I'm going to subtract 3, going to subtract 2, and then I am going to add 18. So this is going to get me 20, which means that t will be negative 5. So now if t is negative 5, all we need to do is find the points, or find the point. So what's really nice about this is that we can now use the parametric equations that we were given. So if we know t is negative 5, well, the x component is going to be kind of nice. So the x component is now negative, or sorry, not negative, it's just positive 11. The y component is still 2. And the z component is now going to be 1 plus negative 5, which is negative 4, which means we found our point. The plane and line intersect at the point 11, 2, negative 4. Look at that. That's all there is to it. Isn't that great? That's great. Awesome. We're going to keep going. I know this section is really, really long. This section, I believe, normally takes us almost a whole week to cover, simply because it's very, very intricate, and there's a lot of important concepts that we must be able to extract. Okay, so one more, or a few more things that we want to work on. So here we go. On this example, we want to find the line of intersection of the planes 3x minus 2y plus z is equal to 1 and 2x plus y minus 3z is equal to 3. So that's what we want to do. Find the line of intersection of these planes. Alright, and so to find out what it is that we need, or to find the exact values that we need. Okay, so I need to find the line of intersection. So that's one of the key takeaways. So what do I need? I need to find the equation of a line. So finding the equation of the line, I need a directional vector. And I also need a point on the line. So those are the two things that I need. Now, one might be easier than the other or vice versa. So we want to make sure that we start extracting everything that we can observe. Notice we are given two planes. So naturally, what can we extract from two planes that are given? Well, we can extract a normal vector. So I am going to say that I'm going to extract normal vector 1, which is going to be for the first plane. Coefficients are the components, so that's 3, -2, 1. And I also have a second normal component, and that second normal component is going to be the vector, which is component-wise 2, 1, -3. Now, what do these vectors have to do with what it is that I'm looking at? I want you to try to envision this first. You have a plane, and within that plane, you have a line. When you have a plane and that line, your normal vector is orthogonal to any line on that plane. So keep that in mind. Normal vector is orthogonal to the plane, hence normal vector is orthogonal to any line on that plane. Secondly, when two planes intersect, their intersection is a line. Let's use GeoGebra for that. Here we are. Two planes intersect, they intersect at a line. A normal vector to one plane, because that line intersects both planes, that line must exist on both planes. Hence, both normal vectors must be orthogonal to that line. Keep that in mind. Both normal vectors will be orthogonal to that line. So here we go. Both normal vectors are orthogonal to that line, which means if we want to find a vector in the direction of the line in question, all we need to do is find a vector that's orthogonal to n1 and n2. So what's that vector? You could call it A, B, C, whatever it is that you want. In this case, I'm going to call it V. I need vector V. Vector V is going to be orthogonal to both of these vectors. Okay, so here we go. 3, -2, 1, and then 2, 1, -3 for the n2 vector. So here we go for the I components. The I component, that's going to be 6 minus 1, that's 5, minus the j component, that's going to be -9, minus 2, that's -11. Good so far. Keep going. Plus the k component. The k component is going to be 3 plus 4, so that's going to be 7. So we have our directional vector. That directional vector is components 5, 11, and 7. So we have a directional vector. Next, we need a point on the line. So a point on the line, wow, that's going to be a little bit tougher than what we have, or than what we've seen before. However, one of the nice aspects about this is that you can choose an x, a y, or a z value, fix that y, that x, y, or z value, and then solve for the other two. If the point that you choose satisfies both equations, then that point is on the line. Now, because lines in R-space 3, or lines in general, contain an infinite amount of points, lines or parametric equations of lines are not unique at all. Which means everybody in the class could possibly have a different equation of a line, and everybody could be correct. Okay, so we got to keep that in mind. So what I'm going to do here really quickly is I kind of see something happening. Okay, look at my z values. If z values cancel, so if I make the z values 0, and again, I'm just using a hypothetical situation here. So if z is equal to 0, what are we left with? Then we're left with 3x minus 2y is equal to 1. And we're also left with 2x plus y is equal to 3. Now, just doing some really quick mental math here, I'm trying to see if I can get this some way, somehow, so that I can find an x value and a y value that will be real nice, that will just get me an evaluation of 1, and for the second equation, an evaluation of 3. Try x is 1. And y is 1. I think that should work. And that gives us all the equations. That gives us everything. So I found the point on the line. By trial and error, the point on the line is 1, 1, 0. Now again, this is not the only answer. You can take the same approach for the x's, take the same approach for the y's. Maybe you don't want to fix z is equal to 0. Maybe you want to fix z is equal to 1 or z is equal to 2, whatever that may be. You are more than welcome to try any one of those values. However, for the purposes of moving forward, we now have a directional vector and the point on the line. So notice they didn't tell us how they wanted the line of intersection, either symmetric equations, vector equation, or parametric equations. So I'm going to start with vector equation first. So my vector equation, I need the original point in vector form. So that's going to be 1, 1, 0 plus t times the directional vector, and that directional vector was 5, 11, 7. Oops. There we go. And this is again for the t values that are unbounded, but they take on every single value. So this is one answer. You give me this answer, if I didn't specify for any type, you're good. You got full credit. Now you give me parametric equations. You give me 1 plus 5t. Y is equal to 1 plus 11t. And z is equal to just 7t. Well, you give me these parametric equations, and you get yourself full credit. If you then instead give me parametric equations, that's fine as well. X minus x naught, so x minus 5, or sorry, wrong one. X minus 1 divided by 5 is equal to y minus 1 divided by 11, which is equal to z minus 0 divided by 7. If you give me the symmetric equations, you got full credit as well. That's awesome. So check that out. That is really great so far. Now, on the exam or on the quizzes, you might get a question that says, how would you attempt to graph the equation of the plane? Well, if you're attempting to graph the equation of the plane, my suggestion is to find all of the intercepts. Find the x, the y, and the z intercept. In other words, in one component, make x, y 0 and find out what z is, and repeat the process for x and y. You'll find those intersections, hence you found the plane that can now be drawn through those 3 points. So, I thank you all for joining me, and this is where we are going to stop it on this particular lesson. So I hope you all enjoyed this, which was the equations of lines and planes. I will see you all for the next one, which will be quadric surfaces. Have a great day.